Okay, so this is joint work with Christian Genet, who was supposed to attend but couldn't finally, and Joanna Neslova. So it's about copula inference for discrete or mixed data. And in fact, it's for any kind of data. So yesterday we learned about continuous distributions. Here it can be discrete, a mixture of that, anything. So first, a little data set. So it consists of the famous horseshoe crab data from Agresti. So here you have 5 random variables that were collected. So some are discrete, some are continuous. So you have the color, 4 categories, spine condition, the width of the carapace, which is continuous, number of satellites. So I will not describe that because there are young people in the audience. And the weight. Okay. So first, is there dependence between these variables? Well, I will try to answer that. How can one detect dependence where you have a mixture of mix of continuous and discrete variables, which is the case here. So to analyze this data set, when restricted to females weighing at most 2 kilograms, Casey suggested to use some extensions of, I'm losing this, some extensions of Spearman's rule, okay? So he concluded that the dependence between x1, x2, and x4 was not significant at the 5% level. So question is, can we do better than that? You can easily guess the answer. So let's talk about the copula. So we've learned a lot about extreme, but yesterday we learned a little bit about copula. So copula is just a distribution function on the unit square with uniform marginals. So then you have the Sklar theorem, which says that basically for any distribution function x, any distribution function h, you can have the following equation. So h can be written as the copula evaluated at the marginals. So F1, Fd are just the marginal distribution of H. So they can appear as limits of points in H. So if the margins are continuous, then of course the copula is unique. And then the copula is just the distribution of the following random variables, U1, UD, where Uj is Fj of Xj. Okay, so if the marginals are continuous, then these guys are all uniformly distributed. In fact, this is a if and only if. So what happens when you have a discrete distribution? Of course, this is not true. So there must be a way to get something uniform back, okay? So the answer to that is something called the psi-transform. So at least it appears in the paper by Ruschendorf in '76, but maybe it's originally due to Ferguson, so I don't know if somebody has the answer for that. So the psi-transform is just the following thing. So if you have a marginal Fj, so it will be the left continuous limit of f at x plus v times the increment. So it will be fj of x minus its continuous left limit. Okay? So if you have jumps, if you have no jumps, if this is continuous, then of course this is always 0, and this is fj, so this is the same as f of j. So the proposition is nice, is that if you have a uniform distribution which is independent of xj, then psi xj of xj is uniformly distributed. So this is basically the analog of the usual transform. So using that, you can generate uniform marginals. Okay? So Ruschendorf showed that basically if you have a vector now with a distribution d, which is a copula basically, on 0, 1 to the d, then the copula CD defined as the distribution function of U's here. Basically, so the joint distribution of these guys is a copula, and it satisfies the scalar equation. So for any multidimensional distribution over the unit square, if V is independent of X, then the copula CD associated with the distribution of these guys satisfies scalar equation. Okay? It's not known if you can get all copulas that satisfy the equation through that transform. I tried to prove it, but well, I thought I did it first, but I don't think it's true. Anyway, it would be nice, but it's not really important. So the important thing is that when you take D to be independent, the independence copula, or you take the V's to be independent in uniform, then the resulting copula is called, it's denoted by C Maltese. So it's called either the multilinear, the checkerboard, or the Maltese copula. Okay, so it is well defined. And this copula satisfies always the scalar equation there. Okay? Let's just recall that the psi-transform only depends on the marginals. So C Maltese is well defined for any distribution. If H is, if the xj's are independent, then the C Maltese is the independence copula. And this is only true for that copula. So if you take any of these guys here, in the independent case, you won't get the, you will not get the independence copula usually. And in 2007, Johanna showed that basically the C Maltese is the right choice for in the discrete case. So through some properties of dependence measure and so on. Okay, so for example, what happens if you have count data? So integer value random variables. So in that case, if you have U1 to UD independent standard uniforms, then the copula is just the unique distribution function of this one, these guys, x1 plus u1 minus 1, etc. With marginals f1 Maltese to fd Maltese. So you look at this, the distribution function h Maltese of this, you look at the copula is nothing but the Maltese copula. And here, of course, because you add continuous random variables, then the margins are continuous. So the copula is unique. Okay, so there's also a relationship between contingency tables and the Maltese copula in the discrete case for, in fact, the empirical Maltese copula. So if you have empirical data, of course, you can treat this as in the discrete case with a finite numbers of values, and you just define the Maltese copula as before with the empirical distribution. So suppose that you have a K by L contingency table. You denote by the F are just the frequencies, and Fk dot is the sum over all the frequencies for the, from 1 to K. You have A dot L also defined that way. So in this case, Cn Maltese corresponds to the empirical distribution function Hn. It has a density with respect to the Lebesgue measure, and it can be almost everywhere defined by setting that, well, in fact, the density in that case is just the frequency, the FKL over the product of the margins. And this is true for any U in this interval and any V in this interval. So outside the density is not well defined, but it gives a density of the empirical Maltese copula. Okay, so now relationship between this and other dependent statistics. For example, if you look at the chi-square distribution for a finite number of cells, then it can be written as an integral of the density of the Maltese copula. You have also the G statistics, G square statistics, which is basically an entropy measure, and it can be written as also in terms of the Maltese, the empirical Maltese and its density. Okay? So Spearman and Kendall statistics can always define that way too. So they are basically defined in terms of the empirical Maltese copula. Okay, so what is the main contribution? In fact, I have only one result. Okay, here. So I'll talk about the asymptotic behavior of the empirical copula for any dimension, any age, including continuous or not margins. So Cn hat is just a consistent estimator of the so-called multilinear extension or checkered copula C Maltese. And the main result is about the asymptotic behavior of, so you want to approximate the unknown Maltese copula with its empirical counterpart. You multiply by square root of n, and voila, you got the asymptotic behavior, which will be kind of Gaussian in some sense. Okay, so some notations now. L infinity is just a space of, it's not the space of continuous function, it's a bounded functions. I changed the space before, so sorry for that. K is just a compact set here, and Fk, which just does, will give you the supremum norm. So for any j for which the partial derivative exists, we write Cj dot as the partial derivative. B sub C Maltese is just a C Maltese Brown bridge that is a continuous Gaussian process with the following covariance. Okay? So there's no way we can get this Brown bridge as a limit. You will see why. And in fact, the limit of the empirical copula will be expressed in terms of a multilinear transformation of this process. So there's some kind of convergence problems because even if the simple case where the distribution is discrete, then the except, for example, when in the independence case, the density, the Maltese copula will not be differentiable everywhere. For example, in the discrete case, it's only differentiable in this open set. Okay, and this set depends on the margins. Okay, so because otherwise it's kind of easy to see that it won't work. So the convergence of Cn can be established in L infinity k for any compact subset of an open set. And basically it defines the projective limit topology of L infinity of O, where O is an open set. And this symbol denotes weak convergence. Okay, so you can see that outside that set, at least in the discrete case, the partial derivative doesn't exist, okay? And in fact, at these points, the limit is not Gaussian. You have to take into account the right and left limit of the derivatives, and you got the positive part and the negative part of a Gaussian random variable, so it's not even Gaussian. Anyway, it's not really a problem, as we will see. So the only theorem is the following. So suppose that you have an open set of 0, 1 to the D. So I don't include the boundary. So suppose that it has a Lebesgue measure 1. So this is not required, but it helps in looking at some interesting statistics. So on that set, we assume that the partial derivative exists and are continuous. And there exists a mapping which is called a multilinear interpolation operator that depends only on the margins. So that, in particular, for any C that satisfies the Slaughter equation, MF of C is the Maltese copula. Okay? So you got your Brownian bridge here, and you define C Maltese and not C at Maltese as the transform of B. So basically, if you take, for example, in finance, often you got some returns that can be zero. So it means basically that the overall distribution is not continuous, but has a jump at zero. So in that case, the set will look like that. So here it will be F1 0 minus, and here it will be F1 0, and then F2 0 minus, F2 0. So here, for example, the open set could be the union of 4 sets, this one, this one, this one, this one, and this one. Okay? So basically, here you won't get, the derivative won't exist. Same thing here, same thing there, there, and there. Okay, so the open set depends on the margins. So you depends also what kind of distribution you have. So the result is the following. As n goes to infinity, Cn at Maltese goes to a process C at Maltese in LO infinity, meaning that for any compact subset K of O, it converges in L infinity K. And C at has the following representation, which is basically the usual representation of the limiting copula for in any case. So this will be C Maltese minus kind of Brownian bridge, one-dimensional Brownian bridge processes times the partial derivatives. And here, in fact, beta J Maltese is just C Maltese evaluated at 111 UJ 1111. Okay? So if you look at the interpolation here, you have your process, and then the multilinear extension in that region, it's easy because it's just a linear interpolation in that region. Here it will be something that is quadratic. Linear, linear, and linear. Okay? So, of course, in the inside, the derivative will exist. And in fact, it's, the density will exist, and it's constant. Okay. So this is the main result, finally. So it can be straightened if in the special case where they are independent, of course. So in that case, suppose that C Maltese is the independent copula. Then you have the convergence over L infinity 0, 1 to the D. And here you will, the partial derivative in that case are easy to compute. Okay, so it's the product over U case for K different from J. And here you have exactly the same processes. Okay, so one can ask, is there a problem having only the convergence on an open set? The answer is no most of the time, except if you believe that, for example, the Kolmogorov-Smirnov is a good statistic, which I don't believe, based on many years of simulating powers of test of independence and so on. So in that case, I cannot prove well, maybe for a kind of approximation of a Kolmogorov-Smirnov, I could prove the convergence, but not in the usual case. So the main theorem characterizes the limit of the empirical process on L infinity K for any subset K of O. And also I can prove, which is kind of interesting, that the supremum norm of the empirical copula process is tight. Does it mean that it converge? It's tight, okay? So although you don't have the convergence on 0, 1 to the D, so the result is sufficiently strong, for example, to deduce the limiting behavior of any, most interesting functionals for copula inference. For example, Spearman's rho, Kendall's tau, Kramer von Mises type statistics. This is basically because if you look at the definition of the statistics, you can write the integral over O because O has Lebesgue measure 1, and then you subtract it's basically these are all in the integrals, so you just integrate on a compact set, and the difference between the open set and the compact set can be made infinitely small, and due to the fact that this is tight, then it's negligible. So basically, you just have to look at the convergence on these subsets. So for example, for the Spearman's rho, still have time. So Johanna has proved that basically the right definition of the Spearman's rho is the following. It's just 12 times the integral of the difference between the Maltese copula and the independence copula. So this is the definition, the theoretical definition of the Spearman's rho. So the empirical counterpart is easy. Rho n is just the same, but replacing the, you just have to replace the copula, the Maltese copula, by its empirical counterpart. And in fact, you can show that it's nothing but the rank-based statistics where you look at the mid-ranks of the xi's and the xj's. So for example, in R, when you want to compute Spearman's rho, you can ask for mid-ranks and all kind of stuff. So now, from now on, you choose mid-ranks, okay? This is justified. Okay, so proposition is the following. So rho n minus rho Maltese always converged. And the expression is nothing but 12 times the integral of the process over O, okay? And because it has a measure 1, so it's no real problem. If you have independence, then the variance is 144 times the product of these variances. So if you recall that in the continuous case, the real variance is 144. Because F tilde and J tilde are just F and J, and these guys are, in fact, it will be 112, it will be 1, the variance. So these guys are uniform. And F tilde is just the average of the left limit and the right limit. And it's nothing but the expectation of the psi-transform for V, which is uniform. Okay. So also, you have the same kind of computation that you can do for Kendall's tau. For Kendall's tau, you can show that it can be expressed as -1 plus 4 times the integral of this expression. Okay? And in dimension 2, it converges weakly to a centered Gaussian random variable, which has the following expression. And in fact, if you have independence, then you recover exactly the same kind of limit as in the continuous case, which is that this limit is 2/3 of the limit of Spearman's rho. So this is always true. Just the variants that are a little bit different. Okay? So a test of independence could be based, for example, of the Kramer von Mises, which is my favorite statistics, by the way, if you did not guess yet so far. So can be shown, for example, that Sn converged to S, which is this integral on 0, 1 to the D. Here, because it's under the independence, I can integrate over 0, 1 to the D. And it's a powerful test because Sn over n converge in even if the independence, even if the independence does not hold, then Sn over n converges to this, which is greater than 0 if H0 is not true. So this is a consistent test. So in particular, a test based on Sen is always consistent against any alternative. Okay, so problem is that the limiting distribution, even in independent, rewind, even in the independence case, depends on the marginals. So if you want to look at the asymptotic distribution of the statistics, you need some kind of bootstrap. So the bootstrap here that we propose is based on multipliers. Johan talked about, well, mentioned the term this morning. So it's a very powerful technique. And basically, you just have to define IAD random variables with mean 0 and variance 1. For example, it could be plus or minus 1, probability 1/2, or Gaussian. And then you define these functions that are necessary anyway to compute the statistics. And basically, you can show that if you take the xi's, which are basically your multipliers, and you subtract the mean and you multiply by these guys, the asymptotic limit will be exactly the same as the process. Okay, so you can bootstrap the process without knowing the marginals and so on. And you can approximate, for example, Sn by Snm, which is the integral of this process. And it's kind of easy to compute. So then the p-value of the test can be approximated by this. Some numerical experiments. So we choose 5 copulas, independent Clayton Gaussian, with different values of tau, 4 kinds of marginals, binomial Poisson, geometric, denoted by F1 to F4, 3 statistics, RSN, the chi-square, a modified version in R, which accounts for Monte Carlo. Sample size was 100, level of the test 5%, and we used 1,000 multipliers and 1,000 repetitions for the simulation to be able to compute the power and the level of the test. So the test base, we will see the results after that. So basically, the test based on Sn maintains their nominal level vary in every scenario. The standard chi-square it performs poorly except when the margin is F1, which is finite in that case. Even resulting to Monte Carlo, it improves the level of the test, although it's slightly liberal in some cases. The power of the test based on Sen is way better than the other two for almost all scenarios except 8 and 10. But in that case, the chi-square is cheating. Okay, the level of the test is around 10%, so you cannot compare them basically. So this is the table. Don't ask me how to do that with the color. I will answer by a question, how can you get rid of that color? I don't know, okay? So maybe it's a particularity of Beamer, but... Okay, so finally, when you want to test for independence in a multivariate setting, which means basically d greater or equal than 3, a very powerful method is to use what we call a Mobius decomposition. It was introduced in dimension 3, basically, by Bloom, Kiefer, and Rosenblatt. And also, I think in the general case, you mentioned something like that in the 80s, maybe, I don't remember. But you will see the definition anyway. So it's a very powerful method because in the independence case, you get a bunch of processes indexed, or a bunch of random variables indexed by all subsets of 1 to d. And in the limit, all these statistics are independent. So there's a very good way to, based on the Fisher transformation, to combine the statistics into a very powerful independence test. Okay? So for more details, paper with the Christian in 2004 in the general case for time series, or the usual case, and there's a package by Ivan who basically help you to compute everything there. Okay? So with these values, you can compute the p-values, and the graph of that is called the dependogram, which is quite interesting. For example, if you have the one copula that is called the Farley-Gombel-Morgenstern, which is a very kind of weird copula, which is defined that way, all pairs of variables are independent, so, and the triplet only exhibit dependence unless theta is equal to 0. So you take any pair here of uniform, they are always independent. Okay? So I generated a sample of size 1000, and then I computed the dependogram for that. And you will see that indexed by the subset, the all subsets, so you have 4 subsets here, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Then this is exactly what you have. So you have very small p-values here. This is so small that you cannot see it, I guess. This one is a little bit larger, and this one is within the interval of confidence. But this one is very large. So you kind of detect dependence within this. If you use, for example, any method based on correlation, of course the answer will be that you cannot detect dependence, because all pairs are independent. So it's also true for Kendall's or Spearman's rule. Okay, finally, let's go back to the horseshoe crab data. So when the data are restricted to large females, then in Kesey, he based his test on the Spearman's rule, so it's not very powerful. But if you look at the dependogram, you see that you detect dependence, okay? And then you also compute the statistic Sn, or its Mobius transform, and you have p-values which are very, very small. So basically, you detect dependence within this data set, even if you have a mix of discrete and continuous random variables. Okay, so the message is that you could base your test of independence on Sn instead of the chi-square, for example. And for multivariate data, the Mobius transform is a very, very powerful method. And that's it. Thank you.